Do inpainting yourself. Generative facial inpainting guided by Exemplars. We present EXE-GAN, a novel method that can complete the facial image with exemplar-like facial attributes. Our core idea is to encourage networks to learn the style of facial attributes from the exemplar in a self-supervised way while guaranteeing the natural transition across the inpainting boundaries. Starting from the input image, our method can edit the eye style, the mouth style, and the hairstyle from exemplars. Hairstyles can be edited with the insertion of basic sketches. We first describe the framework of our exemplar-guided facial inpainting. Given a masked face image and a binary mask, the encoder of the multi-style generator outputs a global style code as well as the corresponding multi-resolution feature maps. Simultaneously, a mapping network linearly maps a randomly sampled latent code to a stochastic style code, and a pre-trained style encoder directly maps an image to a disentangled style latent space. We employ style mixing on stochastic and exemplar style codes, and modulate them with the global style latent code of input image into the multi-style generator for facial inpainting. Next, the decoder of the generator utilizes the multi-style vectors and the multi-resolution feature maps to generate the output. Now, we describe how we optimize our networks. Given the ground truth image and the confidence weight, we employ the spatial variant learned perceptual image patch similarity loss to constrain the perceptual similarity between the output image and the ground truth. To generate visually realistic images, we use the adversarial non-saturating logistic loss with R1 regularization for generative adversarial training. To learn the style of facial attributes from the exemplar image, we equip our proposed self-supervised attribute similarity metric with reverse weight to measure the consistency between facial attributes of the inpainted result and the exemplar in the style latent space. Moreover, we constrain identity similarity between the output image and the exemplar image in the embedding space. Spatial variant gradient layers, SVGL, are utilized for natural transition across the filling boundary. Next, we describe how the spatial variant gradient backpropagation technique adjusts the loss gradients. Given a binary mask, we generate a confidence weight mask and a reverse weight by using Gaussian smoothing. To address the issue of visual inconsistency on the filling boundary, a novel spatial variant gradient layer, SVGL, is designed to impose the spatial constraint on loss gradients in backpropagation. In forward propagation, SVGL does not change any information for the output image. In backpropagation, gradients are re-weighted based on the spatial variant weight mask and reverse weight mask, respectively. Here, we show comparisons to state-of-the-art methods. Here we compare our method to state-of-the-art free-form inpainting methods, including globally and locally, partial convolutions, gated convolution, and co-mod-GAN. We also compare our method to guidance-based facial inpainting methods, such as EXE-GAN and LaFan. Here we compare our method to star-GAN v2, mask-GAN, and sim-swap for the facial attribute transfer. We further compare our method to Liu et al.'s eyeglasses removal method. The results show that our guided facial image recovery method performs well on removing tinted eyeglasses and sunglasses, which may fail with Liu et al.'s method. Now we demonstrate a number of applications by equipping our generative facial inpainting method. Our method can be used for local facial attribute transfer guided by various exemplars. By mixing the style latent codes of two exemplars, our method achieves blended styles of facial features. Given a masked image with hair sketches and an exemplar image, our EXE-GAN produces an style-edited output. Our method can also recover facial images from occluded eyeglasses and masks by masking them out and taking the same person as the exemplar.